On behalf of my colleagues Assad and Immo, we are responsible for deploying a huge amount of our software in the institute, and we are doing this on top of our scientific work. So we are not administrators, but developers. And so I want to start with a few words on dependency management. Why is it necessary? Typically, the dependency management is done by the normal users, which means the users that have maybe a bit of knowledge of it, but oftentimes none at all, have to do the installation of the software themselves, and therefore have issues with linker incompatibilities, have issues with the flags they have to set, and we have to help them. And this is a major time sink. So I guess many of you already faced it when you had started your PhD. Your first task was install Patsy. And that's it. And now you're there and, okay, how do I install Patsy? I go to the site of Patsy, download it, and it's not working directly. So I'm trying and trying over and over again till it's working. This is maybe feasible for a tool like Patsy, but now I have the coder, our fluid solver, which has 440 dependencies, or the whole FlowSim stack with 200 dependencies. Now trying each of the dependency to get it compiled is not feasible at all. On top of that, it's not that we all have these dependencies. Now we want to use different compilers. We want to use the GCC on the one, we want to use the Intel on the other machine. We have different libraries of BLASK or LAPACK from different vendors. We want to use different MPIs. We want to compile the program with OpenMP support, with Int64 support. And you get the idea, we want sugar on top, it's exploding. And we have to handle all of this, and we have to test all of this, and it has to come together somehow. And of course, we have a lifecycle management. We need to build and run all of the software. We need to document how we build them and how it's working. And Immo already presented earlier this morning, or earlier in this symposium, that the first paper of Tau was published in the 90s. And it's still running up to today. And when someone is coming and telling me, I need a Tau version that's 20 years old, please compile it for me. To figure this out, how to compile the old version, and I don't have a colleague who has done this. Of course, this is pretty complicated and would be another huge time sink where I need weeks, if not months, to get it compiled on our new cluster. That's why we decided to go with a package management tool called Spark. And we started with that in 2021. And there we had the first commit for the Tau. And since then, we can guarantee that we can compile of the Tau versions. So our overall goal with this dependency management manager is to have this build reproducible in a really easy way. You just run one command and you get the full configuration of all of the dependency stack with the right configuration. We want all the variants we have. If I wanted to have it with MPI, all the dependencies have also the MPI, and the user does not have to do anything with it. You just say, I want to have the package, and everything is installed for you. Of course, this also allows us to have all the old configurations and all the old configurations of the code to have compilable with our package tool, because inside the package tool, we have the configuration of the former time. It also abstracts the build system away, which allows the user to use the tool without having any idea how the build system itself works. And it allows us as the developers of these packages to also fix quirks or issues with the build system in our packages. So what are the main steps to get this running? We have to specify where we get the software. We have to specify the dependencies of the software. We have to specify all the flags and how it is built. And we have to do it for each version. So this results in a lot of effort. And most people say my software is working out of the box. There is no issue. While this is true for some of the software like Python, OpenMP, and ParaView, where a lot of experience is already in the build system, but also many different build systems, I still have to know how this build system works. I don't have to fix anything on the builders itself. I don't have to apply patches. But this does not hold true anymore if I go to some advanced frameworks. Patsy, I already mentioned it, maybe is working, but already there, sometimes you have to fix some stuff by hand. But stuff like OpenBlast or Cassiope coming with an own build system, and really complicated, there's a lot of stuff you have to fix. So it's not running out of the box. So I'm going into the code, fixing stuff there, and this becomes even worse if I go to our specialized software. There, like Tau, Trace, Coda, all of the stuff, I always have to fix something. Some of the releases have bugs in it, so we have to fix the bug, and we are not able to wait till the next release is coming to fix the bug. It has to be released right now, and so we have to apply patches there. In order to do all the stuff, we went with the software called Spug. It's designed to have different compilers available for the software using different MPI, the different Flask versions or LAPAC versions. Right now, it has over 7,300, or around about 7,300 packages already done. So they are all available in the main repo. It supports a lot of build system, even rarely distributed ones like WAF. The syntax is on the Python style, and it's it's DLR wide available already, and becomes the standard for our software deployment. Of course, to be fair, there are different tools than Spug. A pretty well-known one is EasyBuild. There are no major difference between Spug and EasyBuild. Some minor differences are that EasyBuild is not going with the default like install or configure commands, but have weird different commands. I don't even remember them. A second thing is it supports the up or head. EasyBuild only has an RPath support since the version 3.52, and it's not activated by default. This might result in really, really large module files. And then there's a second tool based on the Conda. Often the Conda versions like Anaconda come with license issues, so we have to pay for the license. And that's an issue for us because we don't want to pay. It's no binary package. It can be done with effort, but still we don't want to put it in. But it's meant to be integrated with a pre-installed MPI and CUDA or compilers, which reduces some of the work. We decided to go with the Spug. And it has more or less 4 simple components I need for the basic package. This means I need to define the build system. For example, the Python-based PyTool or PySetup, the pip, the WAF, the CMake. A download location like the Git repository, a version and a checksum for security and for identification. And then, of course, the whole dependency stack. Then I can give some variables, like I want to have it done with OpenMP. I want to have it with sugar on top. And then I can apply patches. And then at the end, I can give the build system the flags I need for the building. And then everything is stored in the package for the different release versions. And I have all of my knowledge in this package, and the next one just can use this package to install all the already implemented versions. Now I talked a lot about patches. What does it mean with the patches here? For example, in the 8.0c library, we fix some headers or some libraries. The Cassiope needs some syntax adjustment for the Python part. We need to add some flags for the Tau code. The mums needs to add the OpenMP in the linker. And the Sultan doesn't come with a package file, so we need to add a package file. This is all one patch I'm writing. I have it there right in the top. It's like a Git diff. I just apply it. The code is adjusted. And now everything should be working out of the box. And you don't have to care about it. You don't have to fix ever one of the build system because Spark is doing it for you. Currently, we are at 95 patches in our repository. And I told you all of these, if you think 1 minute for each patch, then we're over an hour at work to patch all of the dependencies here. They are often for specific releases, and many of them are patched later on. So if I take the newest software, then the issue is not there anymore. But the specific software version, this has an issue, and we keep the patches for them. And so this allows us to install our whole fleet of software, like our lattice Boltzmann solver, our linear solver. And you can see the increasing dependency chain on the left side. It's getting bigger and bigger and bigger. And installing the full dependency chain takes days alone in compile time. We also use this to create containers. We use containers, for example, for our continuous integration toolchain. We have them for every project. They contain all of the dependencies for the project, and they are generated in a weekly fashion. We do the same for deployment development containers. It's exactly the same container like above. And we also have some customers in industry or on the HPC side that are asking for our software. And there we provide them the container. Then you use Singularity or AppTrainer. And it's the same procedure as above. I just adjust the spec recipe to have some of the software they are not have the license for or they don't want to use. It's just a few lines to change, and then I can deploy the container to our customer. So how does it look in the end for our side in the installation? Now we've done all of the package. Then we are using an environment file for the whole installation. We define on top here additional package, additional configs for our environment we want to install. Then we're doing the concretization. The -D means we are using the environment. The concretizer will go through all of the software, will check the compatibility of all of the packages, and then we will generate a config file for the installation. Then we just call the installation. The installation will now pull all of the software, install it, and as soon as it's done, we are generating some lmods. It's not necessary, but some of the users want to still use the module system. This can automatically be done by Spark. And then we make the modules available to the user. So how does it look on the user side? Like I said, we have many users that want to use the module system. So they just say module load and then say which version of the software they want to load. An alternative to that, we can just use the spec load, and then they can use the load the version they want to use. And if the software is missing or too old and they need an update, we provide them with the so-called config scope. I've shown it here in the bottom. Then I can reduce all of the dependency chain or all the software that's already in the dependency chain and pre-installed on our side, and only install the newest version. Here depicted, you're only installing the coder. If you're not using the config scope, then we install quite a few software stacks again. And like I already said, the installation time of days in compiling, we can spare a lot of time by just giving the user the config scope. Yeah, and therefore I want to conclude. Please don't build your packages by hand, your software. The scientific software is not invested or often not invested into software engineering. In the systems, there are flaws. Since we use the package managers, we have 149 packages. It's growing. It will be soon, over 150. We reduced the compilation or the building time for the whole FlowSim universe from weeks to a single day. Normally, I would say everyone can do it. It's pretty easy. there's always someone proving me wrong. The latest changes we added to the features is the config scope. It allows us to add additional software to our environments and allows the user to reuse the software stack. And we made a mirror creation available, which allows us to configure on one machine, copy the configuration, and pull the whole software stack on a second machine and copy it to the first machine again as a mirror, because the first machine doesn't have an internet connection, for example. And it also allows us to build all the stuff on a backend node on the cluster. Then our next goals we want to reduce some of the complexity of the packages. We want to flatten the dependency chain as much as possible and streamline all of the stuff. And like I already said, there's always someone finding a way to mess it up, and we want to make it as foolproof as possible. Yeah, and that's it from my side. And if you have some questions, feel free.